6.3 exponential functions. Linear functions, so that's an equation for a straight line. When the x values are evenly spaced, the y values have a common difference. Okay, so that brings us to this problem. This says, does a linear function fit the following data? So if I plotted all of these xy pairs, if I plotted 1, 4, and 2, 7, and 3, 10, and so forth, would they all line up on a straight line, in other words? Okay, and you could graph them, but you can also do a little test by looking at the differences. So you see how the x's are evenly spaced, 1, 2, 3, 4, 5. It could be by 2s or 10s or anything, but as long as it's evenly spaced. And then you want to look, how are you getting from y value to y value? So what are you adding or subtracting? In this case, 4 plus 3 would be 7, 7 plus 3 would be 10, 10 plus 3 is 13, 13 plus 3 is 16. I've got a common difference here, a common first difference, and that means that it is going to work. If I got different numbers out here for the y's, then it would not be a linear function, but this one is, because the first differences are the same from y coordinate to y coordinate. Okay? Now, that's something from a previous section, but we can use a similar type of test to check if this xy table is going to fit an exponential curve. Okay, so would an exponential function fit this data? And you're going to be looking for a common ratio. So what that means, see how the x's are evenly spaced again. If you use the y's and you'd be adding 3, then adding 6, then adding 12, so you don't get the same common first difference. But if there's another pattern that's happening here, you can multiply by 2 from y term to y term, right? 3 times 2 is 6, 6 times 2 is 12, 12 times 2 is 24, and 24 times 2 is 48. So this is a common ratio here. And when you have a common ratio, that's when you're going to have an exponential function. Okay. All right. So let's take a quick look at an exponential growth curve. Okay, so an example of an exponential growth curve, if you think about the population, the human population on the planet Earth, there's a couple people and it's staying flat for a long time, and then we got the agricultural revolution at some point, and then it starts to go up pretty quickly. Okay, and there's some little divots along the way there, but it's going to look something like that. Okay, an exponential decay curve might be something like the price of a car or a cell phone or something. When you buy them brand new, they're really expensive. Like a car, maybe you've heard, when you drive it off the lot, it loses a lot of value just from doing that. So it's going to lose value pretty quickly, and then it kind of flattens out, something like that. And eventually it'll be kind of worth just scrap metal or something, but it'll still be worth something. And so an exponential decay curve might look something like that. Okay, so a growth curve is going to go uphill. A decay curve would go downhill. Just a basic idea of what these exponential functions are going to look like. Okay, so let's talk about what an exponential function actually is. It's going to have a variable in the exponent. Okay, so y equals x squared. Well, we can see that has an exponent, so I could understand how you might think that that would be an exponential function, but it's not. This is a quadratic function. So this is quadratic, and it doesn't qualify as an exponential function because it has an exponent, but that exponent isn't a variable. The exponent is just a number, right? So you need x usually in the variable for it to be an exponential function. This would be a parabola if you graphed it, right? It wouldn't be one of these kind of curves. Okay, so let's get to the next page here. So just a little reminder on how to deal with negative exponents. X to the negative third is the same as 1 over x to the third. Okay, so you can put 1 over it, and then the exponent becomes positive, and that's considered simpler than x to the negative third. So typically you don't leave negative exponents in final answers, unless it's scientific notation or something like that. But okay, so that one would be 1 over x to the 7th. Okay, just reminding you about that because we're going to start graphing and we're going to encounter some negative exponents here. So we're going to graph y equals 2 to the x. We have two different parent graphs for exponential functions, and I'll show you the big difference between these. We haven't graphed one of these before, so let's just use an xy table. Okay, so I've got these different x's already set up, and I'm just going to think, well, what would y equal if x was 0? Well, then I'd have y equals 2 to the 0th, and 2 to the 0th equals 1, right? And then this one would be 2 to the 1st, so 2 to the 1st is 2. I'll just do these in my head, I won't write them all out. 2 to the 2nd is going to be 4. 2 to the 3rd is 8, 2 times 2 times 2, and 2 to the 4th is 16. Okay, now let's look at when we have some negative numbers. So here I have 2 to the negative 1st. Well, that's where the negative exponents come in, right? This is 1 over 2 to the 1st, so it's 1/2. So I'll just put 0.5 so I can fit it in that table. Okay, so this would be 1 over 2. Okay, when I'm doing 2 to the negative 2nd, that's going to be 1 over 2 to the 2nd, so 1/4, right? See how 2 to the 2nd is 4, 2 to the negative 2nd is 1/4. So I'll put that as a decimal. And then 2 to the 3rd is 8, so 2 to the negative 3rd is 1/8. I'll just put that in as 1/8. And 2 to the 4th is 16, so that means 2 to the negative 4th is 1/16. Okay? And now let's try plotting these. So got the point 0, 1. At 1, 2, 2, 4, that's right here, 3, 8, and then 4, 16 is going to be in that top right corner. So set it up so it just barely fit. Okay, and then as we go to the left, negative 1.5 is right here, and then negative 2.25. It's getting really close to the x-axis. Even closer now, and it's going to be kind of hard to graph, but I'm just putting a point that's really close to the x-axis and trying to get closer and closer as I go to the left. Okay, so now we can kind of see what is happening here. We've got an exponential growth curve. This is going uphill as we go left to right. Okay, so this is a growth curve. All right, so there's also a line that as we go left, you can kind of see these points are approaching the x-axis, okay? And this is something called a horizontal asymptote, and I'll get to that on the next page. But just visually, those points are getting closer and closer to that. They're never actually going to touch the x-axis, because even if I had 2 to the negative 100th, it'd be 1 over 2 to the 100th. Or 1 over, 2 to the 100th, which would be a very small number, but it wouldn't be 0. It would be very close to 0. Okay, so let's look at this one. When we've got y equals 1/2 to the x, I'm thinking, okay, y equals 1/2 to the 0th here. I'll just write that as 0.5 in the interest of space. So 0.5 to the 0th equals 1. So that has the point 0, 1. When I take 1/2 and raise it to the 1st, it's 1/2. When I raise 1/2 to the 2nd, let's think about what that would be. Well, I would square both the top and bottom, so I'd get 1/4, right? So this is 0.25. And then when I have 1/2 raised to the 3rd, I'm going to get 1 to the 3rd over 2 to the 3rd. So this would be 1/8. I'll just write that as 1/8. And maybe you're seeing a pattern here. These are the same numbers again, right? So this would be 1 over 1 to the 4th, which is just 1, over 2 to the 4th, which is 16. So 1/16. Okay? And let's look at the negatives. So when I have 1/2 to the negative 1st, I can think of that as 1 over 1/2. And when you're dividing by 1/2, that's the same as multiplying by 2. So this is going to come out to 2. Okay? And when then I'm going to get 4 here, and 8, and 16. Okay, so it's really, it kind of works in reverse to this one. So let's see. We've got 0, 1 again. We've got 1, and then 0.5, 2, 0.25, 3 is an eighth, and at 4, it's at 1/16. As we go left, we got negative 1, 2, negative 2, 4, negative 3, 8, and negative 4, 16 is in that top corner. It's reversed, right? It's a mirror image of the last one we did. So this one is going to be an exponential decay curve because it's going downhill from left to right. Okay, and those points as we go to the right are going to be approaching the x-axis. That's going to be your asymptote, which we'll get to on the next page. Okay, so just these are our most basic curves, exponential growth curves. Well, exponential curves. This one's exponential growth. This one's exponential decay. So you can tell just by looking at the equation without graphing it like I did if an exponential function is going to be growth or decay by looking at the base. So you just look at the part that has the exponent on its shoulder. So here that's a number more than 1, and then so if my base is more than 1, I'm going to have exponential growth. If the base is less than 1, and it's sometimes you'll have more complicated functions, but it's just the part that has the exponents on its shoulder. 1/2 is less than 1, so then I know it would be decay just from that. Okay. So you might notice both of these functions have a y-intercept at the same place, at 1, right? 0, 1's on both of those graphs. So let's look at these. And when I'm finding the y-intercept, all you have to do to find a y-intercept is plug in 0 for x. Because you know any point on the y-axis would have an x-coordinate of 0 because you didn't go left or right any amount, right? So then we just need to figure out the y. Well, 3 to the 0th equals 1. So my y-intercept there is 1. 4 to the 0th, that also equals 1, right? Anything to the 0th power equals 1. So this is going to be 1, and even negative 72 to the 0th is going to equal 1. All of those have the same y-intercept. The y-intercept can move around when the functions get more complicated, but if you just have a number raised to x, it's the y-intercept is always going to be 0. Okay. All right. All right, an asymptote. This is a line that that a curve approaches but never crosses. On those previous problems, it was the whoops, spelled approaches wrong. I forgot the a in there. That's what happens when I'm writing and talking at the same time. A line that a curve approaches but never crosses. That was the x-axis on the previous problems. Okay. For an equation in this form where you have something added to the end, so notice on the previous problems that we graphed, it didn't have anything added to the end. It didn't have a k value here. So if you look at these, you could write plus 0 at the end, which that's why this horizontal asymptote is the line y equals 0. Okay? But sometimes you'll be adding something else to the end, and then the horizontal asymptote is always going to be the line y equals whatever k is. Okay, so on those parent graphs it was 0, but now I've got, hey, I'm adding 4 here, and so my horizontal asymptote is going to be the line y equals, why did I write 3? Oh, it's early in the morning, making mistakes here. My k value there is 4, right? That's in the k position. I'm looking for what's added to the end. And here I'm going to have y equals negative 7. Okay, y equals lines are always horizontal, and so these exponential functions are going to have horizontal asymptotes. Okay, so let's graph this. So I'm going to start by I'm going to graph the horizontal asymptote on both these problems. So I'm going to think, okay, my horizontal asymptote, I'll just put a to abbreviate there for horizontal asymptote, is going to be y equals 3. Okay. So that means I'm going to put a dashed line here for my horizontal asymptote at y equals 3. There's my horizontal asymptote. On this one, I'm going to have y equals negative 5. So that's down at the bottom of this graph here. Okay. And then let's find the y-intercept for both of these as well. Okay, so the y-intercept, you're just going to plug in 0 for x. Now, we kept getting 1 out for y-intercept on those previous ones, but that's not going to happen because of the plus 3 here. Well, 2 to the 0th is 1, but then we're going to add 3 to that. So here my y-intercept is 4, okay? So that's where my curve is going to cross the y-axis. Let's try it over here. So here I've got 3 times 2 to the 0th minus 5. So I'm going to do the exponent first. Then the multiplication, well, 3 times 1 is just 3. So then 3 minus 5 is negative 2. So my y-intercept here is going to be negative 2. Okay. Now let's look at if these are going to be growth or decay. So I'm going to look at the base, just the part that has the x on its shoulder as an exponent. So here, this is my base here. That's a number more than 1. So that means I know this is going to be growth. Same with this here. The 3 isn't the base. Only the 2 is the base here because it's really 3 to the first times 2 to the x. So this one is also going to be growth. Okay, so then I know these are going to go kind of uphill, and you've actually got enough info to draw an okay graph just with the asymptote and that y-intercept, and then you're going to have an uphill curve. Same thing here, you're going to have some sort of an uphill curve, and as we go left here, those points are going to approach that asymptote. But if we want to get more accurate, we can make a table, okay? So I already know what happens. Here, let's make an XY table here. So I'm going to use the XY pairs that are on this graph. So I'm going to go from negative 2 to positive 2. Okay, now I already figured out when x is 0, y is going to be 3, right? Because that was my y-intercept. But let's find the rest of these. So I've got y equals 2 to the negative second plus 3. So that's going to be 1 over 2 to the second, so 1/4 plus 3. So that's going to be 3 1/4 when I add it together, so 3.25. Okay, I'm going to short on space here. And then I'll do 2 to the negative first plus 3. So that's going to be 1 over 2 to the first, so 1/2 plus 3. So that would be 3.5. Okay. So here, let me separate these out a little bit. There's that one, and now let's find. We already did 0th, so let's look at to the first. Well, that's going to be 5, right? Because it's just 2 plus 3. And then our last one. So this is going to be 4 plus 3, which is 7. Okay, and now let's plot those. So we got negative 2, 3.25. It's just barely above the asymptote there. Negative 1, 3.5. It's right here. 1, 5 is going to be here, and 2, 7 is right here. Okay, and then I can see the graph is going to go like this. Okay. All right, so you can always do that XY table on the rest of these. Just in the interest of time, I'm just going to draw a curve with the information I already found here. So I got the asymptote, the y-intercept, and the basic shape here is going to go something like that. And again, I could get more accurate by finding more points, like plugging in negative 2 and negative 1, positive 1, and positive 2 into the equation. Okay. All right, next one. This is the first time we've seen something, an exponent where it's not just x, it's x minus 1. So that's okay. Let's just deal with that, and let's look at what we already know. If you think about what's added to the end, nothing's added to the end. Something's subtracted from the exponent, but nothing's added to the end of the function. So that means my horizontal asymptote is going to be the line y equals 0. All right. Excuse my sniffling, I got allergies. Okay, so y equals 0. And then let's find the y-intercept. Okay, so I'm going to plug in 0 for x to find the y-intercept. So that gives me 2 to the negative first, and I can rewrite that as 1 over 2 to the first, so that's just 1/2. Okay. And the next thing I would think, is this growth or decay? If it's decay, I'd go downhill, but this one is going to be growth because my base is more than 1. This tells me it's growth. And I could make an XY table, but just in the interest of time, going to get an exponential growth curve, something like that. Okay. All right, let's try this next one. So let's see. This is going to give me the horizontal asymptote. So y equals -4, there it is. And then let's find the y-intercept. So I'm going to plug in 0 for x. So I've got 2 to the third minus 4. Well, 2 to the third is 8. 2 times 2 times 2. And 8 minus 4 is 4. So my y-intercept then is going to be 4. Okay. And then I'm looking at growth or decay. My base is more than 1. So that means I'm going to have growth again. Okay. So I've got an uphill curve, something like this. Yeah, and as always, you could make an XY table to get more accurate. Okay, that's the end of the section, and I'll see you next time.